elementary school.
Oh, really? That was unintentionally so loud. I'm so sorry.
I like your enthusiasm. Remember that division in high school works the same way as division in elementary school. Okay, so here we go. I'm going to, in fact, use the same bar that you would have used in elementary school. We're going to write the, well, actually, wait, what is this called? This is called, do you remember what these are called? This is, the thing over here is called the this is called the divisor, because it's the thing that's doing the dividing. Like, it should be called the divider. It's called the divisor, and this is called the, what'd you say? Dividend, underneath the radical, underneath the, what do you call this thing? Actually, this bar over here is called the vinculum, if you wanted to know that. Underneath the vinculum is the dividend. Okay. And above, our final answer up on top will be called the quotient. And if there is, there might be a remainder, right? Okay, so here we go. How many times does 3x go into 3x cubed, we might ask? X squared times, okay. So now we multiply just, again, like elementary school. 3x cubed plus 2x squared plus nothing else. And if you wanted, you could like actually write plus 0x plus 0 if you wanted, but we don't need to. And then we're going to subtract. And we get 3x squared plus 8x plus 7, if you want to write, plus 7 also. You may. How many times does 3x go into 3x squared? That's, like I said, very nice example here we have so far. I'm going to write that above the linear term just to organize my work. Now I multiply 3x times x, 3x squared plus 2x. I'm multiplying x by everything here. I'm going to put in parentheses and then subtract. And I recommend that you use the parentheses and you put the subtraction sign there, even though that part you might not have done in elementary school. And the reason is that this example is nice, and if you omit those parentheses and that minus, you'd probably be okay. But on like the next example where like I have a whole bunch of negatives, it's very super easy. Like a bunch of you will do this on our first quiz. Like we'll make a sign error somewhere. Right? Don't do that. So try and stay as organized as possible. Put parentheses around these. Put a minus sign. Okay. This is 6x plus 7. Is this coming back to you? This is ringing a bell?
Yeah.
Okay. 3x goes into 6x 2 times. So we get 2 times 3x plus 2 is that. And subtracting, we're left with 3. I think just straight up 3. Okay. So, good. It's all coming back. It's all feeling really good.
So, do you just write the remainder as 3?
Yeah, so an excellent question. How do you write the result? And I'm glad you asked that question. Here's 2 ways you can report your result. One way is called polynomial form. And so this might be this first way to write it might be a little more, a little less familiar to you. And the second way I'll show you to write it is maybe more familiar to you. So we could write this way: dividend equals divisor times the quotient plus the remainder. So in our case we just did, we could write the answer this way. And we like this maybe if we're thinking about a polynomial and we're thinking about dividing it by 3x plus 2, then this emphasizes the following fact, which I think is important to capture. And that is that if you were to go backwards now and multiply 3x plus 2, the divisor, times the quotient that you got, and then add 3, you'll get this back, right? So that's kind of emphasizing that piece of it. If you were to do this with numbers, 22 divided by 7, say. Like, what is 22 divided by 7?
Oh, 4.567.
It's, we can write it this way. We can express the result of our division this way. It's 22 is equal to 7 times 3 plus 1. Do you agree? So that's one way to do it. And then the other way is we can maybe slightly more familiar, fraction form it's called. And this is how you might report your answer. If someone asked you it in this way, you might say it's this. It's the quotient plus 3 over the divisor, right? Have you seen it that way? Maybe that's the way you're more used to it. Okay. If you were to write this way, you would write that this way. 22 divided by 7 equals 3 plus 1/7, right? Do you see why they're equivalent though? I mean, they both capture like a different part of what we maybe want to say about what we just did. But if you look at this and you look at this, can you prove that those are equal using one single algebraic move? What did I do?
Divide everything by d of x.
Yeah, just divide everything by d of x. So I want you to understand that like they're really, it's not like two foreign things. They're really saying the same information, obviously. And then I have a cute little question for you. Ready? Read. And then answer. That is, let x equal 10 everywhere in this expression. Everywhere. Here and there and there and there. Okay, everywhere. Tell me what this says. What are you doing? Actually, are you plugging 10 in? So what's the answer to my question? No. So let's actually write out what you get. What did you get here? If you plug 10 into the numerator, what do you get? 3,587. If you plug in 10 to the denominator, you get 32. And on the right side, you get, if you plug in 10, you get 100 plus 10 plus 2 is 112 plus 3 over 32. So what fifth grade problem have we just solved?
3,700.
Yeah, 3,587. What is 3,587 divided by 32? And if you were in fifth grade, you would do it using, I don't know, maybe long division. And this is the answer you would get. And let's just be clear, x, a variable, can at any point in your life that you like can take on a value, right? It's like, though let's not forget that x could be 10. And if so, then we've just answered this along with a million other division problems. Okay? I just want to, at every turn, make sure we're emphasizing the strong connections between the arithmetic of the real numbers and the arithmetic of polynomials, right? There's a one-to-one correspondence. Practice, go. This time, it's all on you. It's still not like crazy difficult, but I did throw a negative coefficient in there, so and things don't work out maybe quite as nicely. But we're still easing you back into this. Maybe been a while. Go ahead when you're done. As you're finishing, you can check your answer with your elbow partner. does 2 go into 7? 7 halves times, right? 3.5, something you want to say. You're not done until you have a remainder that's a constant or possibly 0, right? If your remainder is still linear, then you probably can do more division, is my point, right? Yeah, exactly. That's what I'm saying. It's like so. What remainders? What's the remainder that you guys get? What is it, 9 halves?
Yeah.
Negative 9 halves?
If you get 2x squared minus 4,
So let me make a comment as Isabel's putting this up. Your remainder, and I want you to think with me about why this must in fact be the case. Your remainder should always be, if you're dividing by something linear, like we are right here, listen, if we're dividing by something linear, like 2x plus 1, your remainder should always be, at worst, a constant, right? Now why would that make sense? I'm claiming too, maybe, that if we're dividing by a quadratic, like say we're dividing by 2x squared plus 1, that our worst remainder that we would ever get should be only linear. Okay, so, and maybe it goes back to like the mechanics of how you do long division. If you still have something here, linear at the end, then it means you haven't done enough division, right? Like you can still go. You know something linear? Let's do it. Let's keep going. Don't stop there. Does that make sense? I mean, if you write out the answer with a remainder that's linear here, you'll get something that's true. It's just you haven't done as much division as you could have. Does that make sense? So, if you want to generalize that idea, your remainder should be always at most of degree n minus 1 if you're dividing by an nth degree polynomial. Why don't you just pick whichever form you like best?
Whichever one?
Yeah. Are you doing polynomial form?
Yeah, because it takes less.
Alright, so Isabel has the answer up there. It's got the remainder of negative 9 halves, and she's writing out, looks like she's just going to do polynomial form. We'll skip the fraction form up there, but I assume that you're like able to do that as well. Okay? It's good practice for us, though, to do both ways. Negative 9 halves. If you got negative 9 halves as your remainder, you probably did it right. Like, it would probably be difficult to get that remainder and have done it wrong. Okay. So, moving smartly along. Did everyone need that? Anyone still good? You can write them as decimals. That's fine. Okay. Are you satisfied? Remember one other nuance about long division. Remember that if you have any powers missing, you need to put a placeholder in there, right? You remember that from this your prior experience with this? If you had like if the x squared term was missing from f of x, then you'd have to put in here like 0x squared or something, right? Just ring a bell. So just keep in mind we will encounter some examples like that, and I want to make sure you remember what to do in that situation. Also remember, like, I would make sure you're careful on this work. If you went wrong somewhere, it might have been because of like being off by a negative somewhere, right? So be real careful in organizing your work. Okay, let's talk about 2 theorems that are important to us that connect this to other information that we've been talking about. Let me start by asking you to consider only a divisor of the form x minus a number. That is, a divisor that's like simple. It's a really, really simple divisor. X minus 5 or something. And if we divide by that, we could in polynomial form summarize our result as f of x equals x minus k, the divisor that we've said we're going to use, times the quotient, whatever we get as the quotient, plus some remainder, which is a constant based on the discussion we just had, isn't it? If it's a linear divisor, then we're going to get a remainder that's at most a constant. Then, my question to you is, what is f of k? how can we express f of k, given that f of x we just said is this? Here's f of x. What is f of k? Plug in k. What do you get? Plug in k. What do you get?
That's not funny.
What do you get? It's just r.
R.
Oh. Talk like a pirate day with this past weekend. It wasn't something or
It was like, yeah, we're teaching to get people.
what?
If you dress like a pirate,
Yeah, so this is your opportunity. Yeah, you just get, say it with me, you just get, no, like you mean it. So you get what? R. Okay, there you go. Okay, good. That's very satisfying. You just get R if you plug in K.
Guys, I don't think that was actually true because that would have been bad. What?
All right, so what you've just derived with me is something called the remainder theorem. And it's maybe more profound than like we've just led on. And that's if you divide a polynomial by this simple linear factor x minus k, or x minus a number, then the remainder that you get is simply f of k. Okay, and that's if and only if, actually. Cool. So what does that allow us to do? Well, I could give you a polynomial and say, hey, if I were to divide this by x minus 5, if I were to divide it by x minus 5, what would the remainder be? If I just cared about what the remainder was, you can tell me. It's just f of 5, right? That's what this allows me to do. You might be thinking, like, why? If I'm dividing, don't I want to have the whole process? I don't care just about the remainder. Okay, good question. I think you'll see why maybe in a second that might be useful to us. And this seems like a narrow result. We're only interested in dividing by x minus k. Yeah, actually a lot of times. Whatever we like. Right? So that's what I said. If you're dividing a polynomial by x minus 5, say, then the remainder you will get is f of 5. If you divide f of x by x minus 5, the remainder you will get is f of 5. And we've just proved that to be true here. Okay? Into f of x, whatever you want. So, for example, find the remainder if you divide a function f by x minus k. The remainder is f of k.
Is it like a fast way, or do we have to solve it?
So, yeah, so if I'm dividing this by this, one way you could find the remainder is by actually doing the long division and seeing what the remainder is, right? But the way we've just established of doing this is if I divide this by x plus 3, then what should the result, what should the remainder be? I don't care about the rest, I just care about the remainder. It should be g of negative 3, we have to be a little careful there. It should be just whatever g of negative 3 is. That is, if you like understand that enough to write it down, then you understand the last slide, right? That's the whole point. This is the remainder, whatever it is. So figure that out, and we'll have our answer. Here, the remainder will be, if we divide that by this, x minus 2, our remainder will be g of 2. And down here, g of 1. So compute each of those for me, using your arithmetic skills. Let's see, 9 times 2. Blah, 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 blah. Okay, figure it out. What'd you guys get for the first one? And the second? And the last one? You guys agree with those? Okay, cool. So do you understand, if you were to do the long division, you could just check us on this if you want. You could, if you were to do this, divided by this, then you would get some stuff, and the remainder would be negative 5. Okay? Now we're ready to hear the factor theorem. One of these in particular is of great interest to me. Which one? The second one. Why? Because what does it tell us? If the remainder is 0, then it goes in evenly, meaning that x minus 2 is one of the factors of that. Do you see why maybe we only care about the remainder right now? Is because like we're maybe on the hunt for factors of a polynomial. Like maybe that's what's motivating here. We haven't even come out and say that, but maybe that's what's motivating us to do this. Is that like we're on the hunt for perfect factors. And we just found one, like just because we were trying some values and one worked. Cool. We could, by the way, without using any of this high-powered stuff, we could just factor this straight up too. It's a quadratic, for goodness sakes. Right? When you do that, you'll find that one of them is x minus 2. All right. So here comes the factor theorem. It's exactly what you just said. If the remainder, as in f of k, if that's 0, then it must be true that x minus k is a factor, and the converse is true too, right? This connects in a big way the factorization of a polynomial with its zeros, right? If someone tells me that x equals negative 20 is a 0, then I know that x plus 20 must have been a factor of your polynomial, right? And the converse is true too. So that's like an immediate result from the remainder theorem, isn't it?
You said we're not going to have to do proofs.
I mean, these two proofs are trivial, really. I mean, I proved the remainder theorem for you, right? We just did it in front of you. I said deriving the remainder theorem. And then the factor theorem is an immediate consequence of that. You might call it a corollary to the theorem. That's the fancy word. Corollary means something that's easily proved without any work from a previous result. No, it's called a corollary. All right, let's remind ourselves, please, listen with me, please. Remind me how to do synthetic division. Let's do this. Here we go. All right. Remember this? If, all right, listen. If you have a factor like this, if you have x minus 2, if that's your divisor you're looking at, then, and we often are concerned with a divisor that's really simple like this, as we've just demonstrated, then we have this synthetic division way. It's like voodoo to you, maybe. Like, it just works. How does it work? I don't know, but it does. Let's just practice it, and then maybe you can think about with me why it works at another time here. We're running out of time today, but I know you've done it before, so we'll just do the voodoo. Here comes the black box. And then maybe we can prove on Monday or Tuesday, maybe we can prove why this works. Because it is pretty amazing. It feels like magic a little bit. We write the k value, so if it's x minus 2 down here, we're writing 2. If it's x plus 2, then we'd write negative 2. And then we write, going across the coefficients, remembering again to put a 0 also, if there are any skipped coefficients. And from descending powers in standard form, right? Drop the 3.
Please try the interruptions for a brief announcement.
No.
Congratulations
No.
to this year's senior homecoming court. Anders Alilio, Jack Blitz, Mitchell Dawson, Fundo Candera, Zach Kahn, Christopher Lee, Luis Oriana, Jonathan Ortega, Leo Simon, Julian Watson, Colleen Adams, Mitzi Carvalho, Sophie El-Nasri, Caitlin Faraz, Devin Guest, Angela Kim, Nicole McNamara, Lily Sahakian, Madeline Shuck, and Kimberly Davis. Congratulations, guys. Will all members of the homecoming court please stop by the media center after school today to pick up your biography sheet. Also, homecoming tickets will be on sale Monday and Tuesday of next week. And today's cross-country practice is canceled. Thank you so much. Everybody have a great weekend. Go Rockets!
Go Rockets. All right. So I'm trying to like mime up here as best as possible without overriding the announcements. What happened there? Right? Drop. You like my cloud? Drop, multiply, add, multiply. And if there are more to do, then keep doing that. Multiply, add.
Please pause this interruption also for an additional announcement.
No.
Administration hopes everyone has a fun, safe, and unifying school spirit.
Please don't pack up. I have actually.
Monday is class
I
color
really
day.
want to do 2 more slides.
Tuesday is
Let's see if we can do
tie-dye
one more.
Tuesday or senior toga day. Wednesday is dapper day. Thursday is theme day, and Friday is black and gold.
What did we say the
All students are reminded that there is zero tolerance for bullying or harassment of students during Spirit Week or at any time. Bullying and harassment includes hazing, tagging, or marking students, speaking negatively about a student's grade level, or any action which makes a student feel unwelcome to Richard Montgomery. Hate or face painting is not allowed on campus.
All right, let's do this example here while he's talking, please, if you will.
Coming to school. During Spirit Week, all normal dress code policies apply. This includes senior togas. Not meeting these expectations may result in administrative consequences, which may include students not being allowed to attend the pep rally, the football game, and/or the homecoming dance. Let's get together for Homecoming 2016. One community, one team, one school. We hope to see everyone at the game tonight, and if not, we will see you Monday morning.
Okay, let's do this example. We still have about 2 minutes left. Plenty of time. Okay, so you're putting -3 in. Are you with me on that part at least? And then what are the coefficients going across? 2, 0, 7, -3, 1. And then we drop the 2, multiply, add, multiply, add, multiply, add, multiply. That's okay. 3 times 70 is 210 plus 24 is 234. Okay. Okay. Plus the positive 234, right? 235 is what we get there at the end. Okay. So if we do the division, then we get 2x cubed minus 6x squared plus 25x minus 78 plus, in fraction form, 235 over a plus 3, right? Sorry, those are all a's. The other question here is, what is p of -3? What is p of -3? It's 235, right? Like, that was the whole point of our factor theorem. In fact, so if you plug -3 into this, you will get 235. Yeah. All right. Now, the reason that's cool is because this actually might provide for you. Hey, guys, can you do whatever you're doing quietly? This might actually provide for you a faster way than doing it the traditional way. Like, if you were to plug in -3 normally, that would involve you having to take -3 to the 4th power and, like, take possibly 5 powers of your number. Whereas when we're doing this, even if you weren't doing division, if someone just straight up asked you for p of -3, you might choose to do this. Because all you ever have to do is multiply and add.
Well, that's how we found x.
Yeah, in algebra 2 you might have done that. Sometimes we call that, in fact, synthetic substitution. All right. You can go.